Hey guys, I am Teo Samarđija from Croatia. I am studying computer engineering at the Faculty of Electrical Engineering, Computer Science and Information Technologies in Osijek. And I am about to hold a presentation about programming for the web, for the browsers in your programming language. So, client-side browser code in web apps is usually programmed in JavaScript, and it has been for a very long time. JavaScript, the first browser to support JavaScript was Netscape 2. It was released in 1996. And for decades there was no alternative to JavaScript, so it has a special place on the client side of the web. However, you do not need to write everything or even a significant part of the client-side code in JavaScript today, as many people claim you have to, and that's a downside of making client-side programs. These days it is probably easier to make your programming language run on the web than to make it run natively on x86, that is AMD and Intel processors, or ARM, which are, iOS runs exclusively on ARM, and Android, most Android phones have ARM processors. I know that because I have made a compiler for my programming language. Actually, I made two compilers, one compiler targeting WebAssembly, that is browsers, and another compiler targeting x86. Targeting WebAssembly was significantly easier, and if I can do it, trust me, you can do it. I'm not even able to get an entry-level job as a programmer right now, but I'm able to do such things. So about WebAssembly. WebAssembly was originally Mozilla's standard for textual representation of JavaScript bytecode. But JavaScript bytecode, that is, I suppose you know what is Java bytecode. That is the same thing for JavaScript. These days, WebAssembly contains both a textual and a binary representation of JavaScript bytecode, and the binary representation of JavaScript bytecode is supported by all popular browsers except Internet Explorer 11, and Internet Explorer 11 is quickly becoming obsolete. WebAssembly, so to write in WebAssembly you need to use some tools, and WebAssembly binary toolkit is a feature-rich and a collection of feature-rich and easy-to-use assemblers and linkers that target WebAssembly. There's also Mscripton one of the most popular compilers targeting WebAssembly, doesn't use WebAssembly binary toolkit. It uses its own assemblers and linkers, but they are not as feature-rich. So, how to install WebAssembly? Well, there is a hard way. You can use CMake to compile it from source, but CMake is hard to install properly on many versions of Linux. That is, it's easy to install on many versions of Linux, but it doesn't work without a lot of tweaking, and if you are going to just for installing WebAssembly, it's not worth it. Then there is an easier way. You can download the binary releases from GitHub and hope they will work on your version of Linux. Those binary releases from GitHub for Linux are dynamically linked. They make a lot of assumptions about, well, you having recent libraries on your Linux machine, which you probably don't. I think what might be the best bet in that way is to download the version for Windows and try to make Wine the one of the compatibility layer that allows Windows programs to run on Linux, to try to make it run on your Linux machine. But there is an easy way that is to install Node.js and npm. Those programs work without problems on nearly all versions of Linux. And then you install the version of WebAssembly binary toolkit, compile with mscripten from the npm repository. It's called WABT. So why did I use C++? Well, many successful compilers are written in C++. The early version of the Rust compilers were written in C++. GCC is written in C++, C-lang is written in C++, and so on. And in my opinion, C++ is so successful because it is the middle ground between JavaScript and Rust in terms of strictness. That is, the compilers for C++ usually warn about code smelling code, but they allow you to compile it. So, and Rust often refuses to compile code which would probably run correctly or correctly in the vast majority of cases, in order to prevent bugs, which is, in my opinion, well, very often counterproductive. And the JavaScript, well, as you probably know, JavaScript programs often fail silently due to, well, what would in other programming languages result in a compiler error. With C++, you also, I thought you didn't need to worry about deep versus shallow copying, or so I thought. In reality, there is I'll show you later. And C++ has advanced significantly since C++ 98. Many people, when you say C++, they usually think of some, well, rather low-level language with very little features. That's not the case. The recent versions of C++ support lambda functions, regular expressions, and so on. So I think that when building a compiler, making automated testing would save you a lot of time. Some parts of the compiler, such as the Tokenizer and the Parser, are very easy to test automatically, and you will save yourself a significant amount of time if you automatize it. Of course, some parts of the compiler, such as code generation, that is the part of the compiler that actually emits assembly code, is not so easy to test automatically, so I didn't bother with that, but many compilers do that. My testing code is 385 lines. Also, automated testing helped me a lot, not only to catch bugs in when I was modifying my Tokenizer or Parser code, but also to make sure my compiler code was indeed compatible with different C++ runtime environments. So about the Tokenizer. First, of course, you need to make a tokenizer when writing a compiler. Tokenizer is the part of the compiler that tells other parts of the compiler where one word in a programming language ends and where another word begins. There's a common misconception that you need to learn to use LEX or similar tools to write tokenizers. While they may come useful for making compilers for already existing languages for which you have LEX source codes, in my opinion, they aren't worth learning if you are going to write one or two compilers in your lifetime. I used only C++ standard library, and my tokenizer code is only 256 lines of code. Then you need to write a parser. The parser is the part of the compiler that tells other parts of the compiler which word is connected to each word grammatically. A common misconception is that you need to learn to use tools such as YACC, yet another compiler, or BISON, to write parsers. You don't, they may come useful, in academic studies of parsers, and by the way, I don't like academia too much, to be honest, and I suppose they are useful when writing compilers for already existing and well-studied programming languages. It's also a common misconception among developers that you need to learn to use advanced object-oriented structures such as builders and composites to write parsers. To be honest, I don't even understand the builders and composites, yet I was able to write a parser. I used only C++ standard library, and my parsing code is 964 lines of code, and it is a recursive algorithm using collections and iterators. Then you need to do, after parsing, you need to do some semantic analysis. You need to check for the malformed sentences in programming language that parser does not catch, but which will crash the compiler. And such sentences also exist in natural languages. For instance, more people have been to Russia than I have. It doesn't sound very wrong when we hear it, but when we try to analyze it, you realize it can't be even grammatically analyzed. Then semantic analysis also annotates the types of expressions in the syntax tree. Syntax tree is, well, the structure produced by the parser, and that makes things easier for the compiler. My semantic analyzer is 292 lines of code. Then you need to make compilation context. You need to make data structures that will keep the information about the current state of compilation, information about currently defined variables, functions, structures, and so on. My compiling context.cpp file is 50 lines of code. My assembly code.cpp file is 83 lines, and my tree-root node.cpp file, which initializes those data classes, that is by far the longest. Of those three, it is 824 lines of code. So about the compiler. When in the strict sense, compiler is only the subprogram that translates the syntax tree into assembly code. So the GCC which our developers outside of the compiler would say GCC or Clang is a compiler. No, it's a program that includes the tokenizer, the parser, the semantic analyzer, and so on, and the compiler. Well, there are many common misconceptions about how compilers work. Just like there is a big gap between how computer users think computers work, I think there is also a big gap between how most programmers think compilers work and how they actually work. One common misconception is that you need to use advanced object-oriented concepts such as visitors. I didn't use them, I don't even understand them fully. Another very common, perhaps even more common misconception is that when writing a compiler you need to deal with the bytecode or machine code. Well, that's mostly the assembler's job, not the compiler's job. Sometimes it comes, you can do some in the compiler, but in ideal case, you wouldn't do that. And then there is a fairly common misconception that frameworks such as LLVM make things significantly easier. In my experience, I haven't even managed to compile LLVM, let alone to link it into some of my project. That's how useful it is. And my compiler.cpp file is 3,358 lines of code. So it's a rather long file. So let's go with the pros and cons of writing in your programming language for the web. So one obvious upside is that every programming language has quirks which people do not know about, and those quirks are a major source of bugs in production programs. Of course, programming in your own programming language eliminates those kinds of bugs because you understand your programming language fully, and there can't be a gap between how you think programming language works and how it actually works. And since JavaScript is perceived to be a bad programming language, many people think using Mscripton, which is a modified version of C language, compiles C++ to JavaScript bytecode, makes you better off since C++ is a better language than JavaScript. Well, in my opinion, using Mscripton might even make one worse off, because although JavaScript has many quirks, the quirks of JavaScript tend to be well known to web developers. The quirks of C++, they don't tend to be as well known. So even though C++ probably has fewer quirks than JavaScript has, they tend to be less well known, so they may even have a larger impact on programs. And when programming your programming language, then you have a better understanding of how the environment works. You know how the compiler works, how the linker works, at least what the assembler does when programming in C++. You don't have to know, you usually don't understand those things. Or when programming in JavaScript also, you usually don't understand deeply how browsers work. So here are examples of quirks in programming languages in JavaScript and C++. Up left, you have one of the quirks in JavaScript, which is rather weird, is that sorting numbers sorts them using the sort function, sort method of the array class, sorts them alphabetically rather than by value. It makes some sense regarding how JavaScript works internally when storing stuff in array. It's actually all turned into strings, but that's definitely not what, unless it's a typed array, which was introduced later in JavaScript, but that's definitely not what a developer would expect. Then there is another, I think the most famous quirk of JavaScript is the automatic semicolon insertion. That is when you, after return, that is when between the return keyword and open curly brace, there is a new line character. The parser of JavaScript automatically inserts a semicolon after the return keyword, which often results in dereferencing null pointers, and it's difficult to debug if you don't know that. Then there are some quirks in C++ which I have bumped into while making these compilers. So JavaScript is not the only language with such quirks. So what are the cons of writing in your language? Well, you need to write everything yourself, and this is a major source of time-consuming bugs if you will write programs in your programming language. Also, communicating with useful JavaScript frameworks is not nearly as trivial as it is when writing in JavaScript. When writing client-side web apps, you probably want to use jQuery and similar JavaScript frameworks, maybe Angular or React, and this is not as easy when you aren't actually writing in JavaScript. Also, making a language capable of useful string manipulation is not trivial. My programming language is about as good at string manipulation as C is. It's not very good at it. Also, programming tools tend to have push support for non-C-like languages. You can, for instance, Vim, for instance, text editor and Genie and so on. They support keyboard shortcuts to go to the end of some block of code. But they assume blocks of code are marked with curly braces, which may not be true in your programming language. And I think it looks slightly ugly. So here is an example of here are two examples of what I mean when I say you need to write everything yourself. If you need to write, for instance, mathematical functions, if you are going to target WebAssembly, because unlike x86 assembly, there is no built-in mnemonics for doing sine and cosine and so on. And also, you need to write basic string manipulation functions, because you can't call the methods of the JavaScript string class from WebAssembly. It doesn't support calling methods of classes. It supports only calling functions. I suppose you might want to install my compiler to understand my work better. So how to install my compiler? Well, you need to install WebAssembly binary toolkit in order to use it. You can download the releases on GitHub. My repository is called AEC for WebAssembly in camel case. That means, A, E, and C are capital letters, W is a capital letter, and A is a capital letter, and there are no underscores between them. The Linux executable files there are statically linked, so they should run on a wide range of Linuxes. That is there. It's kind of a question among to publish to on GitHub to if you have Linux executables that you publish dynamically linked executables because they are smaller and so they take up less disk space and less bandwidth. But that works only if the Linux machine the user will try to start that program on actually has dynamic libraries needed that dynamically linked executable assumes are present on the computer. If they aren't, then you are going to waste a lot of time and disk space and megabytes of the internet downloading them. I think it's probably a better idea to publish statically linked executables on the internet than to publish dynamically linked ones if you are going to target Linux. And then there's also a 32-bit Windows executable. It is kind of a costume on GitHub today to publish only 64-bit Windows executables because they tend to be faster on computers that support them. Well, many computers running Windows don't support 64-bit Windows executables even now. Then there is a FreeDOS executable compiled using DJGPP. Now, you are going to, of course, have a very hard time running WebAssembly binary toolkit on FreeDOS, but so that I just wanted to make sure that if somebody tries to use my programming language on FreeDOS, my compiler is not, well, it's the way I made my compiler is not, it's not a barrier to that. And there is also a WebAssembly executable for Node.js, and it should run even on, well, wherever recent versions of Node.js run. It is compiled with new version of mscripten, and it should run on, well, it shouldn't be hard to make it run on Android or such platforms which don't even have x86 processors. And on most Linuxes, the source code of my compiler can be compiled with one-liner. That is in a stark contrast between, well, most compilers. Most compilers, such as GCC and CLang, are, well, very hard to compile on the Linuxes, and I have made sure that my compiler can be compiled with one-liner on any Linux machine that has a GCC C++ compiler or CLang C++ compiler installed on it with one-liner. So thank you for your attention. I will put the link to my work in the description of the video. I hope you enjoyed.